And Lynn, would you like to introduce our guest?
Hey, so as some of you know, dark energy was a topic that was requested by the group. And so there are two relatively new experiments out there that are trying to make measurements about dark energy. First, I tried for one called Plain DES, which is run out of Fermilab, but they said they were going to send a speaker and then they didn't. So after I realized that they weren't going to send me somebody, I reached out to the other one that I actually know a little bit more about, which is DESI, as you see on Francesco's slide here, Dark Energy Spectroscopic Instrument. And they have a speakers bureau and we're very organized. And much to my delight, we're able to find Francesco. Of course, I have no idea how to pronounce his last name, but he's a member of the DAISY collaboration. And so he is going to talk to us all about dark energy. The next slide has his background. So he's from Padua mostly. And Canary Islands in Spain are where they have a big telescope called the Palma. I'm pretty sure, unless those are other islands. But Spain has a very nice telescope that is on some islands around there somewhere. I haven't been to it. And I found it very interesting that he was into hockey and trails as well as clarinet. So I'm looking forward to the talk. And now we can switch to sharing your slides, which maybe Ariana has. No. Okay, I guess you're just going to share your own screen then, Francesco. So take it away.
All right. Can you hear me?
Yes, loud and clear.
Okay, great. So I'm going to share my screen. Okay, let's see. Can you see the presentation full screen now? Okay, great. Yeah, all right. So thanks a lot for the very nice introduction. I'm really excited to be here today. I'm really happy to have the opportunity to talk about dark energy, which is probably one of the most difficult and challenging topics in physics right now to understand. So yeah, I'm really happy to try to give you this overview about this. As was introduced, I represent the DESI collaboration today, which is the Dark Energy Spectroscopic Instrument, and we will be hearing, we'll be talking about this later on in the presentation. All right, so the outline for the talk for today is the following. So we'll have three parts. One first part, which serves as, let's say, introduction to cosmology and the large-scale structure of the universe. We will try to build up some concepts that we will need later on in the presentation. Then a second part, in which we will talk about the expansion of the universe, how it is accelerating, and why we need the concept of dark energy in the first place. And I will conclude in the third part by presenting some recent results on dark energy from the collaboration I'm part of, from DESI, and our recent findings that dark energy seems to be changing in time. Okay, so let's start with the introduction. And the first thing I want to do is to try to build up the concept of the hierarchical structure of our universe. So we are on the planet Earth, which is the fourth planet of the solar system, and the solar system is a planetary system, meaning that it's a bunch of planets orbiting our own star, which is the sun. There are a number of other planetary systems nearby. So other planets orbiting other stars, which are called exoplanetary systems, as you may have heard about. And all these planetary systems are part of our own galaxy, the Milky Way. The Milky Way is a spiral galaxy. So a galaxy, roughly speaking, is a collection of stars, gas, dust, and dark matter. Our own galaxy is a spiral galaxy, meaning that it has the form of a disk, which is essentially rotating, is spinning. So you can think about it precisely as a kind of disk. In this cartoon, you see fairly much in a quite faithful way how the structure of a spiral galaxy looks like, and in particularly how you can identify these spiral arms over here which are essentially regions of a galaxy, of a spiral galaxy, where there's plenty of gas and stars are preferentially formed. So you will find young stars that has just been formed. At the center of the galaxy, there's a region which is denser in stars. And our own galaxy also hosts a supermassive black hole. So we are not going to talk about supermassive black holes today, but yeah, there's evidence for our own galaxy to have a supermassive black hole at the very center. If we get to draw a line from the center towards the outskirt, along a radius of our own galaxy, our solar system is located at about 2/3 of the radius. So at about 27,000 light years from the center. Here on the right-hand side, I have shown an astronomical image of the Andromeda galaxy, which is technically called M31 in the official nomenclature. And the reason why I've shown the picture of this galaxy is that we cannot unfortunately take a picture of our own galaxy because we are inside it. So to do so, we should travel outside, take a picture, and come back, which is not possible. However, we have many reasons to think that Andromeda could be like a twin sister of our own galaxy. So by looking at Andromeda, we can develop a sense of how the Milky Way could look like if we were to look at it from the outside. The Milky Way is not in isolation in the universe and has neighbors. And in general, all the neighbors are organized in what is called the local group. The local group is a group of galaxies of about 50 galaxies, which are gravitationally bound together. I say about 50 galaxies because it's not 100% clear how many are exactly, but it should be in the region of 50. There are three main major galaxies, which are the Milky Way, our own galaxy, Andromeda, the one we have just been talking about, and the Triangulum, M33, and a number of other tinier galaxies, which are dwarf galaxies. Some of which are quite famous, are the Large Magellanic Clouds and the Small Magellanic Clouds. And the local group is not isolation either itself, but it's part of a larger structure, which is called the local supercluster. The local supercluster is a collection of galaxy groups and clusters. It's about 110 million light years across. It is composed of three main galaxy clusters, each of which should be composed of about hundreds or thousands of galaxies. The three galaxy clusters are the Coma cluster, the Virgo cluster, and the Fornax cluster. And our local group is right here, right in the middle. And then the large supercluster, our local supercluster is not in isolation either, but is part of a large-scale pattern. That's why we call this large-scale structure of the universe. And the local supercluster is at the intersection of these kind of filamentary structures, which we call cosmic filaments. And cosmic filaments and their intersection, which are typically clusters, surround larger spaces, larger regions in the universe, which are essentially devoid of matter, which we call cosmic voids. So if we get to go through this in one glance, and in the opposite direction, when we look at our universe in its entirety, and we start zooming in, we first find the cosmic web. So this pattern of filamentary structures over here of the large scale structure. And when we zoom in the intersection of the filaments, we find the superclusters. So these very large collections of galaxy clusters and groups. Then we zoom in each galaxy clusters, and we find thousands, even millions sometimes of galaxies bound together. And then we find smaller galaxy groups, which are instead a smaller group of galaxies. So from few to some tens of galaxies. And each galaxy, again, it's constituted by billions or even sometimes trillions of stars, planets, and other objects. So once we have built this hierarchical idea of how the universe is composed, we can start asking ourselves, what is the universe made of in the first place? So in our everyday life, we experience life on Earth, so we can only touch what we consider to be the standard matter, so essentially the matter that constitutes the periodic table of elements. However, so while on our a planet, this is 100%, so it's the whole matter that we have available. In the universe, this is only 5%. And the rest is split into about 26% dark matter. It's a percentage that varies between 26 or 27%. Dark matter, we will not be talking a lot about that today, but dark matter is matter that does not emit light. That's why it's called dark. So we cannot observe it directly with telescopes, but we know it is there because of its gravitational effect. So if we go back to our picture of the rotating galaxy, if we were just to consider the matter that emits light, and we will be looking at how this galaxy rotates, we will be observing something very different from what we actually observe. So if we measure how the galaxy is rotating, it looks like there is much more matter than we actually can observe. So the only possible explanation, if we want to preserve the laws of physics that we know, is that there must be some form of matter that we cannot actually observe. And for this and actually many other reasons, we need this form of matter that is there. We can observe, we can detect the gravitational effect, but we cannot see its light. And then, which is the main character of today's lecture, we have about 69% of a form of energy which is called dark energy. Dark energy is dark, so it doesn't emit light either. We essentially don't know what it is. We will try to build an intuition of how it behaves in the rest of the presentation. We don't know what it is. But what we know is that the universe is expanding at a pace which is faster than what we expect. And therefore, there must be some form of energy that essentially drives this phenomenon. This is what we are going to talk about in the next slides. So all these components together gives the name to our standard cosmological model, which is called the lambda CDM model. Lambda stands for dark energy. It's a specific type of dark energy. Again, we will talk about this later on. CDM stands for cold dark matter, meaning that there is dark matter in the universe and it's cold. So it's made of heavy particles. Okay, another important thing that we have to do to be able to understand why dark energy is important is to go through a bit of history of the universe. So our data nowadays seems to point towards the fact that the universe should be about 14 billion years old. And it should have started with a Big Bang, after which there was a very short but very powerful phase of expansion called inflation. And these two phenomena essentially give an initial push to the universe that triggered the expansion of the universe. After inflation, inflation was followed by a phase up to 1 second after the Big Bang, in which essentially the universe was we can think about it as a hot dense soup. So the universe was very dense, very full of elementary particles like electrons, neutrinos, and photons. And essentially these particles were interacting together by bouncing against each other and making like a huge hot dense soup. So we have to keep in mind that the universe is expanding. And while the universe expands, the temperature of the universe decreases. This has very important implications. The first is that while the temperature decreases, all the particles which are around essentially also slows down. And therefore, when the particle slows down and they get closer, there's a higher probability if they are slow that they interact together. And that's why as the temperature decreases, these elementary particles arrange them together and form the first nuclei in a phenomenon in a process which is called nucleosynthesis. So in the first 3 minutes, we get to form in the universe essentially the first main heavy elements that we have in our periodic table. So deuterium, helium, and lithium. After the nucleosynthesis, there's essentially nothing happening, nothing very, very relevant apart this big fog, this big like dense soup, still like with particles scattering off each other until 380,000 years after the Big Bang. At this time, something very interesting happened, which is that the temperature is still decreasing and decreases until when the protons and the electrons are now slow enough to start forming the hydrogen atoms. So now we have like one proton and one electrons get together in one neutral atomic hydrogen atom. And this is very important, essentially for the reason that when this process happens, this process is called recombination. This marks the time before which the universe was very dense and very foggy in some sense, and all these particles were bouncing off each other. After this recombination happening, the universe becomes more transparent, meaning that all the photons, which are the particles constituting our light, they are free to travel across the universe, and then we receive that light. So recombination is the first time at the universe from which we can receive light. We will go through this in the next slides. After recombination, we have the hydrogen atoms formed, but still no stars. So there's a whole epoch called the Dark Ages in which there is no light emitted by stars. And at a certain point, the first stars start to form. Then they arrange them together in galaxies. And all the process of the hierarchy that we looked at earlier starts. So essentially, the galaxies get together into galaxy groups, and galaxy groups get together in clusters, and clusters get together in superclusters, and we have the large-scale structure of the universe forming. So one important fact, as I mentioned earlier, is that the universe is expanding because of the initial push that it receives. But the only force, the only fundamental force that we have acting at these large scales of the universe is gravity. So we have four fundamental forces in the universe. We have gravity, we have electromagnetism, and then we have the strong and weak nuclear interactions. So the only force that is able to have any impact on the scale of the whole universe is gravity, and the gravity is attractive. Therefore, what gravity is doing is trying to pull together towards one another all the galaxies and all the universe, right? So essentially, while the universe is expanding, gravity is trying to slow the expansion down. So it's trying to decelerate the expansion. This is a very important point because it will become relevant later on. I saw there. Okay, I saw there are some comments in the chat. If there is any questions, yeah, please let me know. Otherwise, I get easily lost with the questions. All right. So as I mentioned earlier, recombination is a very important time in our history of the universe because it's essentially the first time in which the universe, the fog lifted, and we start receiving the photons, so the light is able to travel across the universe, and we receive radiation from that. So we go from the hot, dense, opaque state that we had earlier, where photons were constantly scattered off electrons, to a state which, after recombination, light is released. So photons were set free, and they have been traveling through space ever since. So the radiation that we receive from that time, it's called the cosmic microwave background. Background because it's essentially a background, and it's like it covers the whole sky. And microwave, because if we observe them today, we can observe it in the part of the electromagnetic spectrum which correspond to microwaves. This is the latest and most up-to-date map of the CMB, of the cosmic microwave background, from the Planck satellite, which is a satellite that was operating was operated by the European Space Agency. This map essentially tells you what is the temperature of this radiation across the whole sky. The redder parts correspond to region where the radiation was hotter, which means that the matter was denser in these regions at that time, while the bluer part corresponds to cooler radiation, which means that these regions of the universe was less dense when this radiation was emitted. So this, I mean, you see that there are differences here. There are fluctuations. There are some redder parts, some bluer parts. And these differences actually look quite large, but they have been enhanced to look that large. In fact, these temperature fluctuations, which corresponds to density fluctuations, are of order 1/10,000. This means that if you line up 100 soccer fields, one next to the other, these tiny fluctuations corresponds to just walking back and forth about 1 meter. Okay, so that's very, very tiny. Still, what this temperature fluctuation represent, as I said, they correspond to density fluctuations. And these density fluctuation, although very tiny, were large enough to start driving what is called the gravitational evolution of the universe. So essentially, you get in the hotter, in the redder part, the redder regions, you get more matter, and in the bluer regions, you get less matter. And having more matter here is sufficient to start attracting matter from the surrounding regions, and basically get more and more matter in the redder part and less in the bluer, less dense part. So essentially, this redder part served as the seeds for all the structures of the large-scale structure that we talked about earlier. So all those galaxies, clusters, cosmic filaments that we saw in the pictures earlier were created starting from these small, tiny temperature fluctuations. To better understand this, here I will play a video, which is essentially a fly-through in a simulated universe. So computer simulations in which some scientists have simulating all the evolution of the universe from the CMB time, so from 380,000 years after the Big Bang to the present day. And what you will see is that at the beginning, the universe looks very much homogeneous, like if it was a fog. And by the time the universe evolves, it becomes clumpier and clumpier, and all the filaments start to form, and you will see how also the galaxy clusters form and all the structures that we have been talking about. Okay, so here goes at the beginning. As I said, it's more homogeneous. Here we are already at 1 billion years after the Big Bang, and you see that the first clumps, the first filaments are there. Here you start to see some spherical, ellipsoidal, bright regions, and these are galaxies. And galaxies get arranged together into galaxy clusters. And here the universe is already quite well organized into, okay, here. Okay, great. The video stopped. Okay, never mind. I think you got a sense of what is happening. So essentially at the beginning, the universe is more homogeneous, and towards the end, the universe evolves. Okay, good. So are there questions about the hierarchical structure or the history of the universe so far?
There was a question about the filaments between the clusters and the galaxies, which I don't think I answered correctly. So can you say a bit more about how the filaments are formed?
Okay, yeah, that's actually a great question. Okay, so let's see. Filaments. So everything starts from these tiny fluctuations. Okay, so as matter flows towards the denser regions, uh, they start. It collapses not in the same way in all the directions. So it may collapse in all the three directions. I mean, yeah, all the three spatial directions. That forms a cluster. It may collapse along just two directions, but not a third, and this forms a filament. Or they may collapse only along one direction, and that actually forms something that I've not really introduced, which is a wall. So sometimes you in the cosmic web, you find filaments if they are like structures which are elongating just one dimension, or sometimes you find structures which are more like a paper sheet, a curved paper sheet. So yeah, the answer is filaments and paper sheet form, and also clusters form depending on in which direction the matter is flowing in. I hope I answered the question. Okay, are there more questions?
So AJ asked, but why did they flow that way? In other words, like, why are they linear and filament? Like, if you look at the CMB map, it starts out looking all patchy, but it doesn't look like there are any lines anywhere.
Right. So this is a excellent question. So the answer is a bit technical, but trying to simplifying and develop like at a more intuitive understanding. So this has to do of how, so unfortunately, the CMB map gives us just a 2D representation of the distribution of matter, but actually we have to think in 3D. And in 3D, uh, the matter can have, like the matter distribution can have different geometries. And this also defines essentially the geometry of the gravitational force. So depending on how the matter was distributed initially, what is called the gravitational potential. So the way, essentially the geometry that gravity um, follows, in some sense, can be, I mean, can have the geometry that I explained. So it can induce motions preferentially across just one direction, or two direction, or three directions, and that essentially, yeah, depends on the initial three-dimensional distribution of matter and of those patchy structures. And the reason why the geometry of those initial patchy structures can be different itself comes from this epoch over here, inflation, which to explain we have to go into quantum physics, which is a little bit complicated. But essentially, yeah, during this phase, during inflation, there are some process happening that already gives some initial structure, three-dimensional structure to the matter distribution. And it's only until recombination when we see that. But those are essentially created during inflation.
All right, well, I think it's fine to continue on. Thank you.
Okay. All right. So in the second part, we will be talking about the expansion of the universe and why it is accelerating and why we need dark energy. So we introduced the concept of the expansion of the universe in this slide over here, saying that essentially there's initial push that then drives there is the expansion, and the gravity tries to essentially pull galaxies and matter and decelerate this expansion. But astronomers were not at all aware of this, not even one century ago. So the whole story, in some sense, of the expansion of the universe started in 1929, when a very famous astronomer, Edwin Hubble, after which a very famous satellite have been named, He was investigating some objects, some astronomical objects that he thought were part of our own galaxy of the Milky Way and that he used to call nebulae. He was observing them literally at the telescope, and he observed that these nebulae had interesting properties. So essentially, the further away they are from us, the faster they move away from us, which is a very puzzling. It was a very puzzling result at that time. So if we get to represent these results in a diagram, and we put in the vertical axis velocity, so the velocity with which each galaxy is moving away from us, and the horizontal axis, the distance. All the galaxies, each galaxy is represented here by just one point. They are aligned along this straight line over here, which from a mathematical perspective is telling us that the velocity, recession velocity, what is called recession velocity, so the velocity at which they are moving away from us, is proportional to their distance. So it's proportional to the distance through a number, h0 or h naught, which is a fundamental number in cosmology called the Hubble constant, and we will be talking about towards the end of the presentation as well. So in this sense, Hubble himself was extremely puzzled about the result. At that time, people thought that the whole universe coincided with our own galaxy, and he proved just in one go that the universe was not limited to our own galaxy, and also that the universe was expanding. So it was a quite successful breakthrough. If we try to imagine how the expansion of the universe is working, we go back to the early universe, where the universe was smaller and galaxies were relatively closer together. And as space expands, also galaxies move further apart until they get further and further. Or there's an analogy that we can use, which is the one of a balloon. So imagine you want to inflate a balloon, and the outer membrane of the balloon is the universe, and you draw some dots on the balloon, and each dot is a galaxy. As you inflate the balloon, these dots get further apart. And this is essentially what is also happening in the universe with the expansion. So the first big milestone happened in 1929, and it was only until 1998 that we didn't have any further major advancement. However, in 1998, something very important happened, and cosmologists they were investigating the expansion of the universe, and they used supernovae type 1a to do so. So before we go into this, let's spend a couple of words about what are supernovae type 1a. So supernovae in general are stellar explosions, and there are different types of them. Specifically, supernovae type 1a are supernovae originating from a binary system made of a white dwarf and a normal star. A white dwarf is a peculiar type of star that is relatively small. It's quite compact, so it's very dense, and it's quite also cold. A white dwarf has a theoretical maximum mass that it can achieve, which corresponds to about 1.44 times the mass of our own sun. And in this specific case, when there is a white dwarf in a binary system with a star, what it can happen is that the white dwarf start to strip mass from its neighbor and start to accrete mass on itself. And what can happen is that this accretion mechanism goes on and on until when the white dwarf reaches its maximum mass and exceeds it. And when that happens, the white dwarf explodes and generates a very, very powerful and bright explosion called type 1a supernovae. So after the explosion, the luminosity is the energy that the explosion releases per unit time. The luminosity of a type 1a supernovae decreases in a very characteristic way. So if we go and take a picture day by day of the luminosity of the supernova, we will see that day after day it gradually declines. It follows the so-called light curve. But the important fact here is that the maximum luminosity reached by a supernovae type 1a is a kind of a fixed quantity. This tells us that if we were very close to the supernova, we would always know, because it's by and large always the same quantity, how much energy, how bright the supernova is. For this reason, the type 1a supernovae are also called standard candles, and we can use them to measure distances by measuring the apparent decrease in luminosity. So to understand this, we can think about being with a candle in a dark room. So imagine you have a candle and you know how bright it is because you can observe from very nearby. And then you put the candle on the floor and you walk away a few steps. What you will see is that the light from the candle is dimmer than what you remember from looking at that from nearby. And this is due to fundamental properties of light, that the further you get apart, the dimmer it becomes in some sense. So here, what these researchers did was exactly the same thing. So they knew how a supernova, how luminous a supernova should be. And by comparing the theoretical, I mean, how they knew, how they thought the supernova should be luminous to how luminous it looked, essentially they compare the true luminosity with the observed one to try to measure how distant these supernovae were. Doing this, in 1998, a team of researchers used a sample of about 60 type 1a supernovae to measure the expansion of the universe. And what they did was essentially that they knew already the distance of these supernovae, the true distance, from other independent measurements performed in other ways. And then they also measure the distance based on their luminosity. And what it turns out is that these supernovae looked actually at 10 to 15% further away than they should based on their luminosity. And this means essentially that the universe is expanding faster than it should, or better said, faster than it would if we just assume what we said earlier. So that the universe is expanding, but the expansion is decelerating due to gravity. And what they concluded is that the expansion is doing the other way around. So it's accelerating instead of decelerating. This was an extremely important discovery. We could summarize that by saying that exploding stars tell us that the universe is growing really fast, faster than we expected. And there is probably something extra out there besides just what we thought it was there, just light and matter. And thanks to this discovery, these three researchers, Sal Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011, and essentially the dark energy era started. So to try to put things a little bit in order, we mentioned earlier that on large distances, on the scale of the universe, the only known force that is in act is gravity, which try to attract body towards one another, so the expansion should accelerate. On the other hand, there is observational evidence that the acceleration of the expansion, I mean, that the expansion is accelerating, so there must be some unknown force or entity that is driving this expansion and is counteracting gravity. This force is what we call dark energy. Has been traditionally, so for the first years after the discovery, interpreted as something which could be associated with the space-time itself. So theoretical physicists started to think that the vacuum, so the space-time itself, could have some constant energy associated, meaning that in each point of our universe, at all times, there's some energy associated with that, which is the same everywhere and at all times. And so the reason why the acceleration happens is that while normal matter, which is causing gravity to happen, get diluted while the universe expands, dark energy is always constant because it's the same everywhere and at all times. So at a certain point, even though the dark energy is a little amount, it will take over the normal matter. And that's why at a certain point, the universe, instead of decelerating, it starts reaccelerating again. You can think about that with this analogy. So think about a cup full of jelly and raisins. In the early universe, the raisins are in a small cup. They look like a lot. of them. But while we pass to larger and larger cups, the level of the resins must be the same because, how we have said, the dark energy is the same everywhere and at all times. The level of the jelly, while the resins they get diluted, they get less and less, they look less and less. And this is what is happening instead to the matter density. So essentially what happened after 1998 is that there was observational evidence from this experiment about the expansion of the universe should be accelerating. And there was this triggered a lot of investigation in theoretical physics to try to understand how dark energy works. And the first explanation, and the one that has essentially held until essentially a couple of years ago, is that also for historical reasons, dark energy should be the same everywhere at all times, and meaning that essentially dark energy is constant over time. Okay.
So we have about 5 more minutes.
Okay, good. Other questions related to this part?
I've been doing a pretty good job on the questions that came up this time, so I think you should keep going.
Okay, great. Right, so I will try to be so quicker about this third part. So essentially, what is so we have said that the expansion of the universe is getting galaxies further apart. So if you want to understand what dark energy is, what we are trying to do right now is to measure distances at different cosmic epochs in the universe and try to reconstruct how the universe is expanding over time. And this is essentially what we are doing with the dark energy spectroscopic instrument with DESI. So DESI is measuring the positions of over 50 million galaxies across very large distances and is building a very large map. And the idea is to then measure distances and try to understand how the universe is expanding with this big map. Okay, this is a picture of the DESI, the telescope at which DESI is operating. It's in Arizona at the Kitt Peak Observatory mounted at the Maya telescope. And these are other pictures from this experiment. Okay, I will skip this for the sake of time. What I wanted you to, since we have just 5 minutes left, what I wanted you to retain is the following. So DESI has measured, thanks to these big maps, has measured a very characteristic curve or characteristic feature of some curves related to these distances, which is this bump over here. And the position of this bump over here tells us something very important about fundamental physics, because the position at which this peak, this bump happens, is strongly related to the model that we are developing for our universe. We measure this bump, this feature over here, across 12 billion light years, so across 12 billion years in time. And with this, we measure the expansions of the universe at different cosmic epochs. And with this, we were able to conclude something very important about dark energy. So the way we try to understand dark energy is by means of what we call the equation of state. The equation of state is telling us essentially how much pressure in the expansion the dark energy is putting, given how much dark energy is there. And in the classical view that I've told you about, this number, this can be represented with a number which is -1 always, so everywhere at the same time, constant in time. So what DESI found is that number is not actually constant in time, but it varies. And so if we were to represent these results in a diagram, in this diagram, if this was true, if the dark energy was not changing in time, the results, which are represented by this ellipse over here, by the DESI collaboration, should be over here. The fact that this ellipse is very much off this intersection between this dash point is telling us something fundamental, and this that dark energy is changing in time. A very important fact about dark energy, I mean, the model of dark energy also tells us something very important, which is it allows us to compute how fast is the universe expanding today. And the answer to this question is essentially the number that we talked about when I talked about the expansion of the universe, which is the Hubble constant. So the Hubble constant, which is the constant that relates how fast the galaxies are moving away from us, depending on the distance, is also telling us how fast the universe is expanding today. There are two independent measurements of this quantity. One comes from the early universe, from the cosmic microwave background, the background that we saw earlier. And this number is about 67. While from supernovae and from other probes which are more nearby, this number is more something like 73, which in absolute terms, they look similar, but their uncertainty, so the uncertainty associated with these measurements is now quite small, and these measurements are quite precise. So there's about 5 to 10% difference in between those, and this difference is quite important nowadays. So at first, people thought that this difference could just be a fluctuation in the measurement, so a random error in the measurement. But now, the more we measure this quantity, the more sure we are that it's not something random, but it's something systematic. So either is a measurement error that we are doing all the time in either one of the two, or both these probes, or there may be something that we haven't included yet in our model. So there must be some new physics which is also associated with dark energy. So this problem is quite well known in cosmology and in astronomy as the Hubble tension. And depending on which one of the two measurements is true or not, we'll also have to change our model for dark energy. So to summarize and to conclude, so the title of the talk was what is dark energy? And the answer is that we don't know. However, I want you to take home a couple of important messages. So one, the first is that the expansion of the universe is accelerating, and this is counterintuitive with respect to what we would just have if only gravity was there and there was no dark energy. So this cannot happen only with gravity, at least not in the standard way we know gravity. We also thought, after the discovery of dark energy, that the effect of dark energy would be or could be constant over time. But the recent DESI observations indicate that this is not the case. And if dark energy gets disproved at some point, I mean, this is not the only explanation that can be given to the acceleration of the universe. There are others, and the main alternative to dark energy is we could also have to modify the theory of gravity. So we know that the theory of gravity works well for our planet, works well for galaxies, works well for many other objects. So actually for the vast majority, but there may be cases in which we have to introduce some modifications. So I can't answer the question of what is dark energy today, but I'm fairly convinced that someone will answer it during our lifetime. So yeah, stay tuned, and I really hope there will be some exciting advancement very soon. Thank you very much, and I'm happy to take any other questions that you may have.
Okay, thank you very much. I was just trying to answer a little question there. So you might want to glance at the chat, but I think I did a pretty good job with all of them.
Okay, great.
Great talk, great slides. Any last questions for our speaker? Or if you don't like my answers, do you want to ask your question again so that it shows up at the bottom of the chat? Anyone has any more questions left? Oh, right. Well, we got some thanks anyway. Yeah, let's definitely thank our speaker who had to stay up very late in Italy to give us this talk at 1 o'clock in Pacific time. So we really appreciate that.
Thanks. Thank you for having me.
Okay, so Maggie had a question about Olber's paradox versus dark energy. But Olber's paradox existed far before the discovery of dark energy, which was not until 1998. Olber's paradox is a classical explanation for why, when there's so many stars out there, we don't just see stars everywhere we look. Why are there so many empty spaces in space? So, has anyone heard of that before? Besides Maggie? All right, well, I'll let you all Google it and figure out how it all works afterwards. But yeah, it's not necessarily related to dark energy. It is true, however, that if the acceleration of the expansion of the universe keeps accelerating and accelerating, eventually the galaxies will be moving away from each other at faster than the speed of light. Then you won't be able to see the other galaxies. So that's probably what made you think about Olber's paradox, but it's not really the same. Okay, well, Ariana, I guess it's back to you then. And
Yeah,
thanks, Francesco. We really appreciate it. We'll be posting the recording at some future point when Ariana sends the file to our web guy.
thank you.
Did you remind